Okay, so I just want to say a few words to connect a few things here. Hello? So I just want to say a few words to connect a few things here. So as I mentioned this morning, we're moving from the microscopies to eventually we're going to go to OCT, which is another method of still getting ballistic light, so the light's going straight in and coming straight back, and we do that by throwing away all the photons that are diffused. And as Igor eloquently told us, these ballistic photons, after about 1 millimeter or 2 millimeters into tissue-like structures, there really aren't anymore. So we need to start using diffuse optics and so on. And so Matt O'Donnell and David Bowes and others will talk about diffuse optics and go on that way. And many people will introduce some picture that looks more or less like this. So there's a sampling depth. How deep do you want to measure? Okay, and this is a kind of log scale, but it's going up in 1 millimeter, 10 millimeters, 100, and that one is microns, 1, 10, 100 microns. And so you see the confocal microscopy is about a bit better than a micron resolution, but the depth that you see is in most of the tissues we look at less than 100 microns. You get anything useful. And up at the other end you have MRI and X-ray, and they can see several centimeters through the whole body, but the resolution that you get is never better than about 1 millimeter in those cases. And we used to put it like that, but then when we actually started looking at what are the real depths and the real resolutions in tissue, it turns out that they're all above this 200, I probably shouldn't say 200 pixels, I should say that the depth to resolution quotient is always worse than 200. Okay, so you can use any imaging technique you like, but you'll never get more than 200 useful pixels. Right? The resolution will never be more than 200 useful pixels. And that's quite amazing, because now we're talking about confocal microscopy and ultrasound, and we're talking about MRI, where you have protons precessing and RF frequencies shaking them, and you have X-rays, and you even have antiparticles annihilating each other, and we still have all above this 200 pixel ratio. So we're moving through this course from the microscopies down here up through these methods here, which allow us to see 1 millimeter or 2 into real tissue, so we have real blood vessels and so on, a real 3D environment for cells, and trying to get something like cellular resolution, but we just about see cells with optical coherence tomography. We just about get better than 10 microns. And if we want to see deeper than that, we have to use diffuse light.
Martin, sorry, because last night you said this at dinner, and I went and calculated. I object.
Good.
Ultrasound's about 400 to 500.
Okay.
And what it does is shifts that to the right significantly.
Yeah.
So when you're at 1 millimeter, you can go hundreds of megahertz.
And the low coherence surf sources have 1,000.
I think we can discuss it.
But that's a range.
Optical coherence tomography, or I will not finish.
Yeah. No, I will finish very quickly. So I don't want to take.
Okay, so we'll come back to that.
But I have heard that before. But anyway, we will come back to that. But let's see where it is there. Let's prove it. Actually, when I said this first, Stefan Hell came up to me and he asked me about this. But actually, well, first of all, he asked me about this thing, which is a heart rate monitor that we did. But when we talked about super resolution microscopy, it turned out that also falls in this regime here. The farthest they've seen is about 120 microns, and the best resolution they've got in the axial direction now, which might be where we're going to, our argument is going to end. they get about 400 nanometers resolution, best he thought at that time. Okay, so I'm going to finish there, just those couple of slides to try to connect those things, and back to Igor.
Thanks, Martin, but I think my message at the end will be completely different that you're trying to...
Everybody is going to contradict me. See, you invite people over here and all that.
You thought that was going to be unifying.
No, I cannot to discuss or think about. Okay, so and now if you can see, so if we change the size of the particle, and the scattering phase function is changed, and we can see how it influences the propagation of light for the multiple scattering. So remember, for the scattering, for the single scattering, we have like the certain, let's say, distribution based on the scattering phase function. But for the multiple scattering, when we consider propagation through, the actual profile of scattered file will be different. And it's interesting to see that for some of them, this backscattering will less change compared to the forward scattering. The other important issue is when we think about how to describe the dense medium, like tissue-like scattering medium, is okay. So how we can build the distribution of particles. So obviously that in the we're very lucky if we have the medium when all the particles have the similar size, and we can possibly say that it's monodispersed. And if we have the size distribution, we should come to polydispersed. But this could be the homogeneous medium. But we also could have the inhomogeneous medium when there will be the also distribution of particles with monodispersed, uniformly polydispersed, or polydispersed. And thus, obviously that the scattering of the particles will be not the same. And here we should consider this, again, the scattering phase function according to these distributions, and thus, when we're trying to describe the optical properties in that way, in terms of for multiple scattering, it will be also, these issues also should be taken into account. Okay, but in our case, we most time focused on the studies of human skin and how the light propagates through the human skin. And if we consider the skin structure again, you see so that it's very complicated. So first of all, we have the different layers here, and okay, so for example here we have epidermis, and then dermis, and here we have like the distribution of melanin and collagen within the rest of the dermis, and you see so the distribution of collagen is not uniform. So, and here, for example, the collagen bundles are very thin, and deeper in the tissue it's much thicker. So, and thus, obviously, the description of scattering on that bundles should have even different, let's say, description or distribution of scatterers within. So, and the also important issue that we have here some layers, for example, epidermal-dermal junction, and the boundary between subcutaneous fat and the dermis, when we have significant difference of refractive indices. So here, for example, in the stratum corneum, the refractive index is about 1.5. And then here we have refractive index that's about 1.3. And dermis is about 1.4. And thus, when the light is coming to the skin, it's not only scattered, it also has on these rough boundaries multiple reflection and refractions. And also, if you think about the distribution of melanin granules that have refractive index 1.7. So you see, so this structure makes a perfect screen that protects the light coming into the body and protect the light coming out from the body. So, and the the question is how we can first really describe it mathematically, and then to overcome that screen problem. So in our model, we're able to describe with a very simple mathematics all the boundaries and make these weightnesses associated with the actual sizes of skin or this weightness in epidermal-dermal junction. And the other challenging problem is the blood vessels distribution. You know that it's not homogeneously distributed on the skin. For example, in here is just picture shows how the blood vessels distributed in my skin. Human skin is a bit different, so but what we're able to see in human skin, actually this is from skin capillary loops from monkey skin, but it's very similar. So the capillary loops have a quasi-periodic structure that we can describe assign mathematically. But in the dermal layers, so distribution of blood vessels is more complicated with a different size. And but actually, if we think about modeling, that we're able to describe this system in terms of, again, actual physical properties, so we should describe the distribution of blood vessels. So we used the sort of the scheme that basically come from the physiological studies. So when we consider the one layer of capillary loops that is located in the very top part of the dermal layers, then so-called upper blood net plexus, when this low, small arterioles and venules distributed, and these vessels responsible for temperature control in the human body. Then we have deep blood net plexus, which is here, and then distribution of some vessels within the dermis. And thus, based on this distribution, with the actual information from medical literature, so we're able to understand, how the blood distributed through the tissue. And this is like a summary of the model. So we have complicated boundaries, reflection, refraction, scattering, and distribution of blood. So then, we obviously know the main skin chromophores that absorb the light. So what is that? It's again, so we have water, we have oxy and deoxyhemoglobin, which is here, we have melanin and eumelanin, and we have some other chromophores that here is schematically described by baseline. Of course, it's not like that, it's just for simplifying, so here could be some other peaks associated with particular chromophores, like bilirubin, for example. Okay, so, and then, if I want to build the model, I'm able to estimate what chromophores, in terms of concentration, are placed in each layer, and I'm able also roughly estimate what is the thickness, and with known concentration of blood, hematocrit in blood, so the concentration of water, separation of oxygenated, deoxygenated blood, we're able to count then what will be absorption efficient in each layer. So, and this graph is show us this, this actual absorption for each skin layer based on very simple equation that is based on the concentration and actual presence of chromophore in each layer. So we can do the same for the scattering. So by knowing the let's say by known estimated scatterer size within the each layer, so we're able to estimate the scattering coefficient in each layer of the skin. So these parameters we can also measure with known optical techniques. And we're also able, on the same manner, estimate the anisotropy. And thus, when using this Monte Carlo, we're able to predict how the reflectance spectra are changed when the light is reflected from the skin, and we're able also to predict how the color of skin is changed. For example, this picture shows how the color is changed with the changes of melanin concentration in the epidermal layer. So we can able to imitate the actual skin color for different, let's say, distribution of melanin or melanin granules and so on. So the other way is to imitate the changes of reflectance spectra and corresponding color of skin when we change the blood parameters within the particular layer or in the several layers. And thus we're able to imitate, okay, so what happens when the person is running and some additional capillary loops are opened, and we can able to estimate why the color is changed on the red color, and we're able to also see that quantitatively and predict how the reflectance spectra is changed. And this tool is available online that I want to so that you will be able to even try it, but because of no internet, so I can only show it in a static picture. Okay, so we found interesting ways. So if we do these measurements and when we use the particular color scheme to describe the color, so some scheme are not actually shows you the actual color. For example, when we used this one, so the red color that we see by the naked eyes when we do the measurements is not in this triangle. However, when we use this LAB, so it will be touching the this definition. So thus, if you work with color, so just be careful you should know what particular schema RGB or LAB would be, most convenient for you. So in terms of how accurate we are with this Monte Carlo, so this is the result of our initial modeling when we considered how the light propagates through this box of scattering medium. Here is this experiment with the actual size of particle of known, and thus we're able to find the actual scattering phase function that we described. And this result of our simulation for the similar geometry, and you see, so we're very closely able to roughly imitate the propagation of actual Gaussian beam or laser beam through the medium. In terms of accuracy, we also did always comparison with the reflectance of light from the skin. And you see, so with a careful selection of skin parameters, we're able to also to be very close to the results of actual measurements. And thus, with this Monte Carlo, what we can do, we're not able only to imitate the reflectance spectrum, but we're also able to see, okay, so how the light propagates through from source to detector, and actually what sampling volume means, what area the detector is able to see. So it means we're able to analyze where the main signal comes from. So are we really measure here the only capillary loops, or we do measurement of deep tissue as well, and what is the influence from which depth is coming to the detector, what actually the detector is seeing. Okay, so, and again, so this actually we done with a very similar task. So some years ago, our collaborators from hospital, they asked us to develop the probe that will be able to see the changes of blood flow only in this part of the skin. And the question, okay, how I should put my fiber optics on the surface to make sure that I measure the size, that I measure the signal from that side and ignoring the other. So again, the main target of capillary loops, and here, so the question, how the probe should be designed for the very simple measurement, because to avoid the influence of other blood vessels. And here, for example, just one of the simple picture that shows what is the uncertainty. Okay, so if we use this fiber optics somewhere on the surface and we put it like there, or we put it like there. So obviously when the light will propagate through, so we will have the different influence from absorption of capillary loops. And with our technique, we again modeled, how the light distributed through the fiber optics, or if we use, for example, confocal probes, and how we can localize the measured volume within the tissue to make sure that we takes the light from the predictable area. So there also was a number of discussion, about the angles and how the numerical aperture is influenced on that. But again, all this stuff could be predicted with this Monte Carlo, and even more so. For example, if we change let's say here, the scattering with so-called optical clearing, so we're able to see how the, let's say, confocal probing will be localized in the particular area with the changes of scattering and absorption properties of the area from where. Okay, so what I want to say, so the Monte Carlo is a nice tool for description of propagation of light within biological tissues, and it could be used for skin, and we also use it for optical tomography when we just started with, to find out the position of tumors. And we actually developed that technique even in the final stage, and the Philips company was interested to build this optical tomograph for the commercial use. And what is the problem actually? And the problem is that diffusion approximation that we used for this again studies have a limitation. It's able to see, with this image reconstruction technique, it's able to see the object or tumor, which is about 10% of the total volume. Thus, if we have this diameter, let's say 10 centimeters, so we're able to see 1 centimeter tumor. If the tumor is less than that, we're not able to see that with this just mathematical limitation. 1 centimeter tumor, it's a perfectly developed tumor, and physicians don't need any technique. They able manually, even patient able manually find out that something wrong. So the question, okay, so why? Okay, so we developed that. And then when we realized that, so we moved to this technique for brain imaging. And you see, so mathematically it's possible to create another alternative mathematical technique to describe the, quite clearly the brain position in there. And the obvious target is to find out what actually people thinking about. And I think David Bose will talk more about these issues. So, but what we think that this will be a future of measurements of, as we saw in some movies. And again, about the Monte Carlo bit. So Monte Carlo is used here for like a gold standard now to describe the propagation of light within the tissues. And the optical properties that we use for defining the actual, for standardization or for any quantitative assessment are used in the Monte Carlo for the tool. The only one problem is there. So we're able to predict clearly the how light propagated and estimate what area is influencing our detecting signal quantitatively, and we're able to do image reconstruction and many other things. But the problem is that it's very, very slow, this technique. And how we can overcome that? Imagine, so we should every time take a number of events into account and count, okay, so what will come to the detector. So one of the possible way to improve the algorithm, for example, we shouldn't wait when the photon is coming. We're able to, from each point, to consider, artificially you know, what is the probability of photon to be detected from that. And we call it like semi-analytic Monte Carlo. And this is very nice, and it of course increase significantly the calculations. The problem is that if we have multi-layered, it will be quite difficult to predict, you know, this this probability. And okay, so the other way when we did try to you know, to improve our calculations, we considered, okay, how Monte Carlo is actually running on our computers. So we consider standard computer with one core, like, and what happens? So imagine, so you use your internet browser, so you do some work in the Microsoft Word, and you run Monte Carlo and possibly do some MATLAB stuff. So you have also allocate some time on your computer. I mean, your computer allocates some time for your system and some possibly other processes. And thus, for that, the estimated time of one single photon coming to the detector will be about 100 milliseconds. And we need basically 1 million or even more. So with the more advanced computers, when we have 6 cores, so we can increase it 6 times, basically. So if we're smart enough in the programming skills, we're able to dedicatedly arrange in a single core all the processes for Monte Carlo, all the more computer, and this also makes a significant improvement in terms of time for modeling of light. But once, when I saw that my kids are playing on the graphical, you know, on the GPU-based machine, like Xbox or I don't remember, Sony one.
Yes, PlayStation.
PlayStation, yes. So, and I saw that when someone is shooting to each other, so the bullets are going and then reflecting and, you know, going somewhere else. So we did try to do that movie with our, you know, Monte Carlo as well. But it was so slow that it wasn't possible to make it graphical, to show how the photons are really propagating and reflecting. And I thought, okay, how it's possible that these guys are big? And then we started to, you know, investigate what they did. And we found really that they used so-called, not the CPU, they used the graphical cards. So, and this, they called it like GPU, graphical, of course. Okay, so, anyway, so this produced by NVIDEA and CUDA corporation. And what they did actually, they able to artificially separate this in a card, they place it for a number of cores that could be dedicatedly work for each photon modeling. And thus we're able to come to the milliseconds for one photon modeling. And then also, it's not the end of the story. So we found that these guys are so smart, they incorporated the modeling of some mathematical functions on a very low level. And that saved a lot of time if we compare it to modeling on a, let's say, on a MATLAB. So in there, any sine, cosine functions and other will be counted much quicker. And we implemented as well with a parallel programming. Then we're able not to do modeling one photon, but we're able to model number of photons in parallel, and each core could be described for modeling the particular photons. And thus, we do sort of imitation of how the number of photons propagate. So we potentially were able to take the mask or profile of the laser beam and put it on a like a entrance data for the light source, and that would be propagates through the medium in that way. And thus, if you come to this our online tool, you will see there are some different applications. And if you click in here, so you will be able to simulate or make the online simulation in a very quick way. So, for example, so from here, so your data will transfer to the server, and GPU will produce the calculations and then back, and the actual time of modeling here will be shorter than these transactions, especially through the internet connection, if it's not good enough. Okay, so here just a quick instruction. So, for example, you select the application, so then you come into some short description with the references, and then you can change the settings because they prescribed for the standard case and start the modeling, or you can back and choose another application. So, and when you press the button of change the settings, so you'll see for the scheme the table where each layer is prescribed with actual scattering, absorption, anisotropy factor for Meglinski phase function, refractive index, and thickness. So you can change any of this data, you can add the layers, you can reduce number of layers, and that's all possible. So here is how to do that. Okay, you can use your own numbers if you want. So if you don't want to, you can just simply press next, and you come to, for example, in our case, here the blood distribution, or potentially it could be any other chromophore. So again, here we put this melanin concentration in the top layer, and then saturation, hematocrit, this water, and the hemoglobin fraction is considered, how, for example, if we use it for, not for skin, but for animals, so what fraction of hemoglobin in the red blood cell. So and then, if you want to estimate it for the particular probe, so you should put the detector diameter, source diameter, detector diameter, and separation from center to center. And they also could be overlapped if you need to. And detector numerical aperture. For the light source, it will be the standard one. Then, for example, if we want to make a picture, we should realize what we actually want to see. So we want to see, so if we see the distribution on the detector only, or both source and detector, and thus we should put there some coordinates. And as soon as we've done that, so you press the button, and it goes to the server. And now this server is associated with Microsoft, so it's very quick, it's in the cloud. And you will get one of these results, color, reflectance spectra, and distribution of light, or some others. So, okay.
You said that this program, which is accessible by anyone.
Yeah, if you go to www.biophotonics.fi, so there is an access to this model.
You exemplified here these two fibers, so but you also said that it's applicable equally to photoacoustics. So
photoacoustics is not in there yet, so but I didn't say that it's applicable for photoacoustic. I said for the
there was a little icon there. No?
You mean here?
Photoacoustic tomography.
You see, so coming soon.
So, just to follow up to that, because the time domain, right? So, with the photoacoustic, but have you gone to even shorter pulses, like picosecond and femtosecond pulses?
In the model, we can do it.
I know you can do it, but will that be embedded in there too, easily? So you can just define whatever pulses you have to, pulse times and shapes, etc.
Well, okay, so how it works. So we count the trajectories. And if the trajectories is coming, then we're able to prescribe how, for example, pulse of any, broad or short, whatever, so how it propagates and what we will see. We might see
but also I can look at the point in space and say what is the time domain. If I launch at the surface a certain pulse shape, I should be able to look at some point.
Yeah, we can do that, but again, here we input these applications for the, let's say, for the typical or most popular applications. So if you want something specific with a particular shape of beam, with a particular, I don't know, for lighter Gaussian beams, that we also can do. And we have some results, but they're not yet on the web, because imagine, so as soon as we introduced the first model on the web, let's say here, we have a number of visitors on the site, and what they do, for example, they're trying to test us. They will put, let's say, diameter of the detector 0.00000001, and then they start the button. And we, for example, first days we think, okay, 3 days it's counting something, and not coming out, so no result coming out, and we didn't realize why. So that means that someone smart, put us the parameters that will never, came to the detection. And now all this data are limited. But if you have, the particular interest, so we have the description how to contact, and you're able to be signed in, and we can, see how we can create, your own project. So, but we actually, we see in collaboration with Steve Jacques, we think that to develop it's like, let's say, Monte Carlo platform for the needs of biomedical optics and biophotonics. So the reason is simple. So imagine from our practice, so we have some students who come in to do a PhD project to develop, let's say, a new sensor or optimize something. And okay, so they develop experimental system, and on some stage they need validation of the technique. They need to do the phantom studies or Monte Carlo. And they started to, what they do basically, they will, download the Steve's the Convent code because it's available, and trying to modify it. And they don't care what is count really. So if it's count, fluence rate, which is temperature distribution basically, or energy distribution. So it's not exactly the same what is the sampling volume is, or fluorescence, or other issues. And they try to write new code all the time, and then they spend 2 years of writing this code, and then, at the end of PhD studies, we still have not the final product, or it could be postponed. But we have a number of already solutions, and we did try to create the unified model that will be used for free of charge, and even more. So the results that will come out will come in a MATLAB format, and you're able to use this data immediately for your publication based on the Institute of Physics requirements. So all of you will be able to modify it. So that was like behind that. So the problem was that it was only 2 people who built this device, and now we think we can be a bit more enlarged to cover those items that is coming soon.
But in fact, when I was curious, I was about to say that in all these icons, you populate and some will come. The common theme is this structure with the source and the detector. So that's where I spotted the problem. If you move to optoacoustic, they are not like on the same foot.
Right.
This one is one way, the other one is something else.
I'm sorry, Adrian, I'm not so sure. Can you repeat again?
In all these icons, you have a common theme, which is 2 fibers, an emitter and the receiver.
Yes.
Correct? Yeah. So that's your
No, but it's for the particular application. It's for particular application. If, for example, if I choose, let's say, this, it might be not.
You had confocal case, which was not that.
Okay, so we have confocal or we have the fluorescence. Means you can, they're just one fiber or one source definition. So it means you can able to put the normalized beam, Gaussian beam, Bessel beam, whatever, and see how it propagates and what will be the fluence rate for that. So it's not a problem. So if for the photoacoustic.
And you're stealing the confocal collector in this different
fibers? No.
Okay.
So even here, you see, so.
I understood that.
Well, okay, let's see. So, okay, so when you do this problem geometry, you see, so you can say source diameter, detector diameter, and separation between the fibers. And if your fibers have 0 separation, that means you have this formula.
So you can go back to your unique model. Okay, that's nice.
Okay, so That's it. Okay, so and now I'm coming to polarized light. Okay, so what we spoke about so far, so it was the light that have just simple property, intensity. Means we were able to analyze, okay, so how much energy or intensity is coming to the medium and how much intensity is coming out. But we have other unique properties of a light, for example, like polarization. And I think all of you aware, okay, that's this simple technique when we have polarized light and we use another polarizer that we call analyzer, and if we do that, so we will see brighter or darker or images in there. And the question is, should we use polarized light for diagnostic purpose and tissue characterization? And if we go for that, so what polarization of light should we use? So we have like linear polarized light, we have circularly polarized light, and the question, okay, so which one is better to use? And other question is, will be the properties of tissues are similar if we consider the propagation of polarized light in there. And you remember, so when we discussed the propagation of light in terms of intensity, so we refer that we consider the single photons or packet of photons. But here, obviously, that we should use the waves, and we should be more focused on a description of light propagation in terms of waves. And thus, wave phenomena should be taken into account. And what they, if we come in from the simple point to more complicated. So if we consider just the propagation of wave, like a sine function, for example, in a free space. So that will be the simple sine function from source point to the detector, and we will be able to measure the amplitude on one of the axes. But if we, okay, so we're not working here. So, but anyway, so if we consider the medium with absorption, so the amplitude is going down, and depending on the position of your detector, you might see no signal in it. So if we think about the circular polarized light, so there is a similar thing. So if we consider the propagation of a circular polarized light from source to detector, so we will be able to see here X and Y on cross polarized light and the phase shift between them, and the similar will be happened for when light propagates. This propagates through the absorption medium, so amplitude is changed. However, when we think about this propagation, it could be more complicated than that. Imagine here, for example, when we see that this medium have a very specific properties. When light propagates in one direction, quicker or slower than another one. And thus, we will have a very complicated signature, and this is known as a bifringent property of the medium. And depending on where you put your detector aggressively, so you will see different signature on the detector. I mean, different signature. The other important thing is the interaction of light. For example, this picture shows what happened if the linear light is green and circular polarized light, making it sort of interference. So what it will be final product. And it also will be very strange or not simply described signature or product of these two waves. And question, how are we able to differentiate what happened in here is bifringent and what happened in there? So, and for that, we need to, again, to build the strong model, which is, again, in our case, we want to relate it to Monte Carlo, but it should take into account the wave phenomena. And okay, so and I think so we're coming to this 11 o'clock time. So, and if you don't mind, I can stop on that point and continue after the break.
Okay.
And if you have currently questions, I'm fine to answer.
Thank you very much. Very good. So, do we have questions?
You said somewhere in between that you're not really preferring the Russian roulette, or that is might be not ideal. But how do you terminate your photons?
Good question. So we have a number of conversations with Steve Jacques about that. So I'm just back to this description. Okay, so again, so if you do Monte Carlo technique, so you should know, okay, so let me start again. So if you, original one was for energy distribution, okay, so we do the Monte Carlo when we want to imitate the results of actual experiment. When we have light source and we have detector. We send photons here and we want them to come to the detector. How many photons should we send? That's the first question. And the second question, okay, so if the photons is going somewhere else, so how long should I wait for when this photon possibly will come to the detector? What the criteria should we use for cut off of this, modeling process? And okay, so the Russian or survival roulette is we discussed it. So what we do, we used, let's say, definition of Beer-Lambert law. If we have the photon that propagates, let's say, 10,000 scattering events, and for the scattering medium with the even small scattering or absorption coefficient, you can easily find after 10,000 scattering events what would be the intensity or probability that the photon is coming. It will be exponential function of something in the power of 10,000, which will be negligible small. And thus, that criteria could be used for the cutoff. Means when it's 10,000 scattering events, you can stop it. But we use it only for very precise simulations when, let's say, we want to count something specifically. For the traditional or simple one, we do 5 or even 1,000 scattering events, and it's enough for the cutoff parameter. Yeah, but there is a book about the Monte Carlo method that authored by Emil Sobol. So he coming from this nuclear project, and he describing very theoretically with Markov, chains and so on. And he presented there 3 different cutoff technologies: one of the Russian roulette, one of the number of scattering events, one of the number of coming photons and coming out photons. And he's I very like the comments there that he's saying that potentially the combination of that cutoff technique could be used for smart modeling. It depends what you want.
Okay, any other questions? Just before this, you introduced a scattering coefficient and an absorption coefficient, and then a total extinction coefficient. And I think when you presented it, you said that the total extinction coefficient is 1 plus the other. But there is also an interaction between the two. So if you have scattering, you have a longer path for absorption. So how is that accounted for in or we can come come back to us.
Yeah, okay, so we basically use in the Monte Carlo in this one absolutely similar stuff like people do for the radiative transfer equation or even any theory, so except this survival. And also, again, we're able to put here any distribution of light source, actual light source. We're working now on the question of detector sensitivity in terms of let's see, if it's for fluorescence and for some techniques like to count it like in terms of single photons, and or if you come into the CCD cameras, so we also want to incorporate the sensitivity to, again, with the target to imitate the actual experiment. But the description of optical properties, it's no difference. So we use the standard theoretical points that everyone uses. So in terms of absorption, scattering, this reduced scattering coefficient is absolutely as the diffusion approximation you gave us. And I will have an rest of some slides mentioning that.
Okay. Any questions? Can you apply this to a fiber bundle?
What do you mean?
You have these light guides. You transmit image from one end to the other. And there are sources of
You mean can we simulate the image transfer through the fiber?
If you can simulate the problems inside, you have all this crosstalk going from one fiber to the other and disturbing the path in the other.
Okay, so if we have one fiber is here, and we know distribution of light that coming from this fiber with a numerical aperture, and we have fiber there, when we also know numerical aperture. And
yeah, but the model I think should change because you have a long fiber and you don't have this.
You mean what's coming out from the other side of the fiber?
This, let's say, 5 meter of 20.
Okay, in terms of intensity, so the intensity will come. So if you want to see the modes of difference, so no, we don't consider that through the fibers. So we consider it only the distribution of modes on here or on the detector. But it's if you give us the, let's say, equation that describes how they change it, so that's possible to do.
Okay, so Sergey, one quick question.
Yes. What the spatial resolution can you get?
Special resolution?
Yes.
For what you mean in terms of modeling?
With cell size.
Okay, so okay, so it's the right question. Okay, so here, when we're talking about this modeling on a GPU, so we have an actual memory. So if you have enough GPUs, so you can artificially divide your memory, and thus you can vary your resolution from the, from actually any size. Because the point is, okay, each photon when propagates through described in the 3 coordinates and 3 direction cosine. So 6 numbers. Basically. If you want to add the polarized light, there will be another 3. So, and these numbers should be saved in on the actual, memory. So thus, how much memory do you have? So that relates to your resolution. Currently, we do the modeling based on the resolution of standard, let's say, imaging techniques. For example, if optical coherence tomography give us the pixel size, let's say 3 to 5 microns, with ideally, so we use 5 microns. So we can maybe do the 1 micron resolution, but in that case we will consider at the moment a smaller area, progressively. Or if we increase it 1 centimeter, we can see the big one volume, but again, at the moment the memory is fixed for the actual number parameter. But If we put more GPUs, so in that case it will be more flexible system.
Okay, so at this point I just want to remind everybody that it's time to put our posters up, and there's a couple of elements to getting a certificate. This actual course is accredited in our university as a 5 ECTS accredited module, so you could, if you want to, get that approved back home. But the elements to actually getting that certificate include having an acceptable abstract. You've all done that because you wouldn't be here if you didn't. You've all had me annoy you about changing things and so on. And then attendance at the lectures and the hands-on courses. And the last aspect of it is actually having a poster that is acceptable to these good people over here on my left, right? The tutors on the program. So we will have a session on Thursday to have a look at that. So we will head up there for coffee and tea, hopefully, and maybe even a scone if we're lucky, and put our posters up. Be very careful on the wooden area just outside the back door. It's very slippy.
Martin, the lecture also can get